And then they can have phosphates added to them to become high energy molecules. They're intermediates in metabolism. And we'll see that when we look at glycolysis next. Okay, so let's look at the fact that it can be a reducing agent. That how monosaccharides can be reducing agents. Well, here's beta-D-glucose. When it opens up in its ring, when it opens its ring up, it forms D-glucose. Now it's no longer beta because there's no ring to trap it as a beta or alpha. So in the Fischer projection, it's D-glucose. The OH group on the last carbon is on the right. At the top, there's an aldehyde. Allison taught you aldehydes get oxidized to what? Carboxylic acids. They get oxidized to carboxylic acids. The little bracketed O means oxidation. So glucose can get, the aldehyde on glucose also can get oxidized to a carboxylic acid, and it's called gluconate. I'm not too worried about the name here, just that it can get oxidized. When something gets oxidized, something else gets reduced. So we can reduce other things when that happens. It is called a monosaccharide that can open up and form a Fischer projection. Is called a reducing sugar. It is only in its hemiacetal form. Right now, this monosaccharide is in its hemiacetal form. That is a C with an OR and an OH bonded to it. C with an OR and an OH bonded to it. Makes it a hemiacetal. Therefore, it can open up and it can be oxidized. So it is a reducing agent because it causes something else to be reduced. Not only can glucose, who opens up as an aldose and has an aldehyde on top, that can be oxidized to carboxylic acid. Allison taught you a ketone cannot be oxidized any further. You remember that. She told you can't be oxidized any further. But ketoses can, because they're a special case. So we're going to have fructose. It's in its hemiacetal form. So the anomeric carbon, number 2, has an OH group on it. So that means it can open up and it'll form the ketone at the top. This ketone, because you have an alcohol right next to the ketone, can do bond rearrangement and form this intermediate called an enol. And then that double bond, those electrons will move up to the oxygen and form an aldehyde. So you can take, in a basic solution, you can take fructose and turn it into glucose. Because now we have glucose over there. The aldose is glucose. And then that is what gets oxidized to a carboxylic acid. So it's only a special case that this ketone, the ketoses, can be oxidized because the OH group that has an alcohol group on the next carbon next to the doubly bonded oxygen. So it's a special case. Now, why do you care? Oh, well, let's do this first. A reducing sugar is a carbohydrate whose aldehyde group can be reduced to a carboxylic acid. True or false? How many people say false? How many people say true? false habit. It gets oxidized. A reducing sugar is a carbohydrate whose aldehyde group gets oxidized. You go from aldehyde, the aldehyde, that carbon up there, the red carbon, has 2 bonds to oxygen as an aldehyde. Over here, as a carboxylic acid, it has 3 bonds to oxygen. It gained bonds to oxygen, therefore it got oxidized. It was oxidized. Why do you care? Because if you need to check your blood glucose levels, you want to be able to oxidize your glucose. You want to be able to oxidize all the blood glucose. So you stick yourself with a finger, you can measure with a meter. This is essentially what you're doing. Taking glucose, it's mixing with oxygen. So it is going to open up, the glucose is going to open up in its Fischer projection as an aldehyde. It is going to get oxidized to the carboxylic acid. When that happens, it is going to produce peroxide, H2O2. Peroxide is a very strong oxidizing agent. That means it's going to cause something else to get oxidized, and it itself will be reduced. So the peroxide then can mix with a colorless dye. When the dye is colorless, it's in its reduced state. When it mixes with this, it's going to get oxidized, and it's going to give off a color. And you can measure, and then the peroxide will turn into water and oxygen. The amount of dye that's produced, the color change, is what you can read on a meter to find out how much glucose. The more color change is associated with it, the higher your blood glucose is. So it's actually a really important test. You test for this if you have diabetes, to see if you have diabetes, see what your blood glucose levels. Ladies, when you get pregnant, chances are you'll go through a glucose tolerance test, and they'll measure the amount of glucose in your blood as well as how you manage it, how it goes away, how fast it goes away, to see if you've developed gestational diabetes. So that's the first reaction, the oxidation of monosaccharides. Now we're going to go on to the second type of reaction we were talking about, and that's reactions with alcohols. And this is where we can form a polymer. What is happening, when we started, we had a hemiacetal. We had an OR, this is part of the ring, and that R double prime was an H, and that was a hemiacetal. When that hemiacetal reacts with another alcohol, you get a carbon that has an OR, 2 OR groups on it. It has 2 OR groups, and that's an acetal. That is not to be confused with acetyl. ACETYL means 2 carbons. 1 carbon doubly bonded to oxygen with a methyl group on it. Don't get it confused. If we take glucose and react it with a simple alcohol, methanol, it's just a methyl group with an OH group attached to it, that is going to react with the OH on the anomeric carbon. It's always going to react with the OH on the anomeric carbon. And what you'll get is the methyl group will get moved on to the oxygen, the hydrogen will go off and combine with water. So that'll combine with the OH of the alcohol to produce water. That bond that's in red up there is a special bond. It's not an ether bond no more. In regular chemistry, it would be an ether. COC is an ether bond. But in carbohydrate chemistry, we call it a glycosidic bond. Just like in proteins, when we combine 2 amino acids, we formed an amide bond, but in protein chemistry, we called it a peptide bond. So same thing here. Even though it's an ether, we call it a glycosidic bond when it's associated with a carbohydrate. Is methyl alpha D-glucoside a reducing sugar? No longer in a hemiacetal form. It doesn't, that anomeric carbon doesn't have an OH group anymore. It has an OR group. So it can no longer be a reducing agent. It can't open up its ring anymore and get oxidized. That ring is locked in that position now. It can't open back up. So this is a simple glycoside, or a simple termination for a monosaccharide. And this, when you bond two of these, which we're going to see next, we're going to bond two monosaccharides together. We're going to have the same effect. We're going to use the anomeric carbon is going to react with an alcohol off another ring group, and it's going to form a glycosidic bond. It's a bond between the anomeric carbon of a monosaccharide and an OR group. And I already told you that it's an alternate name found in carbohydrates. Okay. Let's look at how this works in when we take two monosaccharides together and form a disaccharide. I've asked you in the to know the three disaccharides that I'm going to present. I want you to know which monosaccharides make it up, and what it composes of, and then what is the glycosidic bond. So, for the first one is maltose. Anybody ever had a malt? A malt, they actually put maltose in it to sweeten it. So it's two glucose molecules. Notice they're alpha D-glucose. Both of them are alpha D-glucose, and they are going to join by their anomeric carbons. So the anomeric carbon of the first one is going to link up and react with the carbon, the OH group off the carbon of the fourth carbon of the second alpha D-glucose. So that's the functional groups that are going to react together. You have a hemiacetal reacting with an alcohol to give you an acetal. And that is going to give you an alpha 1,4 linkage. So the anomeric carbon that was in the reaction was already in the alpha position because the O is going down underneath the ring. And it's linking carbons 1 from one glucose molecule to carbon 4 of the second glucose molecule. That's where you get the 1 to 4. So you define the linkage as alpha or beta. Do you see it going down or see it going up to the oxygen? And then you define the carbons in the two rings that link together. So you can say it's an alpha 1,4 linkage, drawn like that with a comma, or you can do an alpha 1 arrow 4. And again, the product is water. We lost the H off of the oxygen from the carbon off 4, and the OH group off the anomeric carbon to form water. Is maltose a reducing sugar? How many say yes? You're right. Maltose is a reducing sugar because it has the anomeric carbon, number 1 there on this one, is an OH group, so it can open up. It's a hemiacetal, so it can still open up and oxidize. Okay, let's go into lactose. Lactose, some people are lactose intolerant. You drink lactate instead. Lactose is made up of two monosaccharides. So it's a disaccharide. It's made up of beta-D-galactose and beta-D-glucose. These are isomers of one another. They're distereoisomers of one another. To form lactose, we are going to take the anomeric carbon from the galactose and bind it up to the oxygen on carbon 4 of the glucose. Now we are going to call it a beta 1,4 linkage because the beta is defined from the anomeric carbon that's in the reaction. So carbon 1 of galactose is involved in the reaction to form the polymer, form the disaccharide, and it is in the beta form to start with, so it will stay in the beta form when the bond forms. So you notice, you look at the anomeric carbon for the galactose, and it goes up above the ring, so you know it's beta, and it's linking carbons 1 and 4 together. And again, we give off water. Is lactose a reducing sugar? Yeah, because it has a hemiacetal, the anomeric carbon over here on the what used to be the beta glucose, that anomeric carbon is a hemiacetal. So yeah, it can open up and get oxidized. So it is a reducing sugar.
So if it starts in beta, will it always end in beta? And is that the same for alpha?
So we'll say it again.
So you said that this one started in beta and ended in beta. Is there ever a circumstance where it will change?
No, it's all dependent on what is the anomeric carbon, the configuration of the anomeric carbon that is part of the glycosidic bond. So it'll always be, in this case, always be beta because this galactose is beta to start with.
And it will always be alpha if it starts with alpha.
It'll always be like the maltose will always be alpha because it started with alpha D-glucose. So here's one. This is sucrose. This is your table sugar. Your table sugar is made up of beta D-glucose or alpha D-glucose and beta D-fructose. So you're going to combine these two together, but it doesn't look quite like the other ones. This linkage is an alpha 1 beta 2 linkage because it involves both anomeric carbons. It involves the anomeric carbon from glucose and it forms the bond, the glycosidic bond forms to the anomeric carbon of fructose. So because both anomeric carbons are involved in the glycosidic bond, we have to label them. We started with alpha D-glucose, so we started with that. So we start with alpha 1. That's the first carbon there. The anomeric carbon is alpha. For configuration, it's carbon 1. And it bound to the anomeric carbon of fructose, which is carbon 2. And that was in the beta configuration. So we define it as beta 2. So it's an alpha 1 beta 2 linkage. Is sucrose a reducing sugar? No. They're both anomeric carbons are involved in the glycosidic bond between the two. So there's no free OH. There's no hemiacetal. This is as long as this one can ever be. This is as long as it can ever be. Maltose, you'll see, becomes starch as we go through this lecture because we can take alpha D-glucose and keep combining and growing the chain longer and longer. It doesn't have to just stay as a disaccharide. It can become this long polymer and turn into starch. Where this one, that's it. That's as far as it goes. If you have inverted sugar, they call it, and people will sell that. what has happened is they've taken sucrose, the table sugar, and they've broken them apart. Actually, they just have glucose and fructose, and they mix them together in a 50-50 ratio. And it has a slightly different taste than if you would have the disaccharide itself. The average American, as we're coming out of Halloween, headed into Thanksgiving, and then the rest of the holidays in December, eat about 2 pounds of sugar a week. Eat about 2 pounds of refined sugar a week. Table sugar, white sugar. It's been refined and processed for that. Question 5. The glycosidic bond configuration of alpha or beta is determined by the configuration of the anomeric carbon involved in the glycosidic bond. Yes, that is true. Okay, so since we're on the topic of how much sugar we take in, sugar promotes tooth decay. You've heard that since you were itty bitty. Brush your teeth, right? What do you have in your toothpaste that you brush with? Fluoride. It's going to be very important to prevent cavities, because in your mouth you have at least 2 different types of bacteria. One that loves table sugar as its main food source, and that is called Streptococcus mutans. We call it the evil bacteria in this case. The other one is Streptococcus sanguis. That's the healthier bacteria. When you eat sugar, you encourage the evil bacteria to grow, the mutants to grow, and they outgrow the area of the sanguis. So they take up all the room when they do that, and they keep growing and growing and growing. As they grow, as you are sitting here going through metabolism, you are producing a lot of protons. And we'll see how protons get produced as we go through the lectures in this for exam 3. So bacteria, these mutants, are producing a ton of protons. Well, they won't hold it. They don't take and take care of it like we do in our body. They secrete it out into their environment. So you increase the amount of protons in the environment, what are you going to do to the pH? Decrease it. You're going to decrease the pH as you increase the number of protons. And what that does to your teeth is it takes the minerals that are in your teeth. Remember, your teeth are like your collagen, has hydroxyapatite. It has the collagen in there, and it has hydroxyapatite in there to form it and make it hard. So you're actually taking that out, and you get tooth decay. So it starts to dissolve the membrane or the minerals in your teeth. The cool thing about these, you wake up in the morning, or you don't brush your teeth for a couple days, right? I know you've never done that. And you take your finger and you go like this, scrape your teeth, and there's that white bit. Yeah, that's the bacteria that's growing colonies. They secrete a type of sugar, a polysaccharide, a long chain of sugars, and that help them stick to your teeth and stay in place so they can eat more sugar. So when you brush your teeth, you've got to brush them away. You brush the bacteria away. When they form this, they form the plaque, and that's what you're scraping off, which is gross. So how do we remove our bacteria? Brushing and flossing. Go to the dentist. They recommend going to the dentist every 6 weeks. Or every 6 months, sorry, not 6 weeks. Oh, that would be awful. To get your teeth clean. Also, you brush with fluoride in your in your toothpaste. And if you grew up in a city, you have fluoride in your water. Ann Arbor puts fluoride in their water. I was in the country, so sometimes when you're in the country and you grow up, they'll give you fluoride tablets to take, or give you fluoride treatment when you go into the dentist to help remineralize, to promote remineralization of your teeth. The bacteria do not like to be around fluoride, so they die. They start to die off, so you reduce them. And also the fluoride reduces the solubility of the enamel in the acid, so it'll replace the OH group that's in your teeth. The hydroxyapatite portion has an OH group in there that's negatively charged, has one negative charge. The fluoride will replace that and make your teeth stronger. So that is why the municipalities, they found out a long time ago, adding fluoride to the water helps improve mouth health. Eating candy can cause the bacteria that feed on sucrose to increase their numbers and subsequently cause tooth decay by changing the pH in your mouth. True. Oh no, I did all this work. Let me see if I have another. I did a bunch of work on this slide, and I changed computers, and I don't think it saved it.
Oh no.
Oh, that's horrible.